Next, I would like to thank our YouTube viewers. Thanks so much for subscribing, viewing the videos, leaving comments, etc. We greatly appreciate you checking out the channel. And we've barely even gotten started. We are far from full time at this point, folks. So don't forget to press like and subscribe if you enjoy the content. And don't forget to tell your friends, your foes, your science noobs, and your science pros about the channel. Lots of content besides daily space weather, cosmology, and meteorology segments on the playlists, so check those out. Again, thanks to our subscribers on YouTube. Thanks to our BitChute subscribers as well. There's exclusive content there. And we like to stream live to Twitch. By the way, we'll be streaming live at the moment of the solstice. So on June 20th at 11:32 and 9 seconds p.m. Eastern Daylight Time, we will be streaming. So make sure you join us for that. We'll be on multiple platforms, at least YouTube and Twitch, possibly also Facebook. Before we do the cosmology segment, I'd invite everybody to view our own website and welcome you to the Neo-Renaissance. smAshomash.com, smAshomash.org will redirect you. You can find our social media there. Let us know in the comments what your favorite social media is. We are on many, many of them. And again, you can find links there. Check out our merch as well. It's of very high quality, like our patrons, the main source of funding for the content. And please consider becoming a patron if you'd like the earliest alerts and so on. Also multimedia and all kinds of other science articles nobody gets access to. I mean, they get access to, but do they really understand how it ties together with the other information? Maybe they do, maybe they don't. Patreon.com/smAshomash for some insight you may not otherwise get. So today's cosmology segment is absolutely fascinating, just like yesterday's. If you didn't watch yesterday's, check out yesterday's cosmology segment. YouTube.com/smAshomash/playlists. What about the possibility of helium rain inside Jupiter and Saturn? So there is a new frontier going on right now in science, folks. The frontier of material science is superionized high-pressure materials. It's pretty interesting that common elements, when experiencing millions of atmospheres of pressure, turn into superionized metals and form into a superionic liquid state. They turn flat black. They behave like superconductors. So perhaps have this read about how there are metallic fluid rains caused by the high-pressure environment at places like Jupiter and Saturn. This article on the phys.org's Astronomy and Space section. And also perhaps check out this article here. It's a PDF you can find, The Physics of Superfluid Helium. Kind of interesting, to say the least. So maybe have a read on that as well. It also includes your helium phase diagram. Today's random number is 565, which coincides with this object. It's a high-mass X-ray binary. And I didn't memorize the name. To quote Einstein, never memorize anything you can look up. Anyway, here it is in X-ray. That's from the XMM Newton, and we're not going to see this in very many different wavelengths as it's in a very busy part of space next to a giant cloud of hydrogen. Here's the infrared spectrum, and you can see how busy that area indeed is. And let's see if it shows up in red light. And perhaps that's both stars of the binary there. I have a feeling one is dark and one is light. So that's today's, quote, random, end quote, object. It's Swift J1633.8-4724b. Here are the X-ray transient outputs from that. It's a pretty inconsistent X-ray source. We've only got a very limited amount of data on this one. Looks like not even a year of data on this X-ray source. If you want to look up your favorite transients, head to the Neil Gorell Swift Observatory. For example, if you want to look at Sagittarius A stars outputs, type in SGR space A. It'll link you to number 705. And there are the X-ray emissions from the core of the Milky Way galaxy, Sagittarius A star. And by the way, if you're wondering what Sagittarius A star looks like, the area around Sagittarius A star, that's what it looks like. It's being orbited by a series of supermassive stars, blue supergiant stars that are so big that if they were in our solar system, they would be about the size of Mars's orbit. In other words, you'd be inside them if they were in our solar system. These stars orbiting the galactic core, Sagittarius A star, at relativistic speeds, hundreds of kilometers per second, only a few years periodicity in some of their orbits. So the cores of galaxies are very complex places. The Milky Way galaxy is a very complex place, and that is the sort of thing going on in the core of the Milky Way galaxy. Next, talking about magnetism in the sun and coronal mass ejections and magnetic bubbles and reconnection and so on. Now, we regularly look at GONG hydrogen alpha imagery. It's part of our bonus features on the daily. Reconstructing topology, magnetic topology that is, of on-disk solar prominence bubbles. Another article in the phys.org's Astronomy and Space section. Some three-dimensional magnetic modeling here of magnetic reconnection events associated with the ejection of plasma filaments. So this one may be interesting to you, especially if you're unable to forecast coronal mass ejections. So check out that article there in the phys.org Astronomy and Space section. And we've got a radio telescope here, AVRO. Yes, AVRO, showing up in the NASA astronomy picture of the day. So here is a total lunar eclipse, along with phases of the moon, along with an image of the Owens Valley Radio Observatory, AVRO. So that's today's astronomy picture of the day. You can look at it yourself and others at apod.nasa.gov. And yesterday we talked a little bit about the wobble of the Milky Way galaxy, as all orbiting objects, all rotating objects precess, meaning if you spin a top, it wobbles. And that's kind of important because, well, it's associated with a couple different things. So, regarding the behavior of black holes, they have a hard state and a soft state. In their hard state, shown here, their jets emit X-rays. In their soft state, their disks emit more various aspects of the electromagnetic spectrum, and there is a relationship in that when they go into a hard state, they emit less radiation from their disks, and when they go into a soft state, they emit less radiation from their poles. It's because there's an inverse proportional relationship between the output of the poloidal fields, which are these fields, and the toroidal fields, which are the fields in which you live, the donut-shaped magnetic fields, which are a net result of the overlap of these poloidal fields, the fields from the poles. So here's yet another article about this. Another article from the phys.org Astronomy and Space section. It was quite rich in interesting material today. Similar states of activity identified in supermassive and stellar mass black holes. Now, this is a situation here, folks, where black holes and stars seem to have a lot of similar properties here. Does this tell us some insight into how the sun's behavior is? Well, it certainly does. So perhaps check out this article as well, another phys.org article in the Astronomy and Space section about the way supermassive black holes appear to behave the same way as stellar mass black holes. Supermassive black holes are as massive as billions of times the mass of the sun. At those massive radio sources, stellar mass black holes are as little as 2 solar masses estimated mass. Another article here about the soft state versus the hard state and the proportional relationship between the poloidal and toroidal fields of stars. That's today's Cosmology segment. We hope it was as fascinating as yesterday's. And we'll have to say goodbye to Twitch as we continue on with the daily space weather.